Far across the void, among the stars of the Leo constellation, lies a world that should not exist. A planet orbiting a faint red dwarf just 124 light-years away, hiding secrets that could upend everything we think we know about life in the universe. Scientists have been watching, measuring, analyzing, and what they have found is unlike anything they expected. We have always assumed that life beyond Earth would be rare, fragile, and confined to familiar conditions. That life requires sunlit surfaces, oxygen-rich skies, and water just like ours. But K2-18b challenges every assumption. Its atmosphere is thick, hydrogen-rich, and unlike anything in our solar system. Its chemistry hints at processes we barely understand, and perhaps, just perhaps, signs of something more. Among the water vapor, methane, and carbon dioxide detected, there is one molecule that stands apart. A chemical signature that, on our planet, can only be created by living organisms. Could this be the first authentic fingerprint of life beyond Earth? Could we finally have found proof that we are not alone? Like and subscribe to the channel as tonight we journey into the skies of K2-18b. We will unravel its alien atmosphere, explore the molecules that defy explanation, and confront a question that has haunted humanity since we first looked up at the stars. Is life on Earth unique, or is the cosmos already teeming with it? Prepare yourself. The search begins. The narrative begins in 2015 when Kepler Space Telescope initially identified this mysterious world while systematically searching for planets around distant stars. Though it appeared routine initially, this detection would prove extraordinarily significant. K2-18b wasn't just another planet. It might unlock the universe's greatest enigmas. Visualize a world completely unlike our solar system's inhabitants. K2-18b is classified as a subneptune, situated perfectly between rocky planets like Earth and gas giants like Neptune. Its radius measures roughly 2.5 times Earth's, with nearly 9 times our planet's mass. However, its location makes it truly special. K2-18b exists within the Goldilocks zone, neither excessively hot nor cold, but ideal for liquid water. The planet circles its red dwarf star every 33 days, meaning a K2-18b year equals approximately 1 Earth month. Despite this proximity, the star's cool nature provides roughly equivalent light and heat to what Earth receives from our Sun. Here's where things become fascinating. K2-18b isn't rocky like Earth or Mars. Instead, it represents an entirely new category of potentially habitable planet scientists call Hycean worlds. The name combines hydrogen and ocean. These planets feature thick hydrogen atmospheres above massive liquid water oceans. Traditionally, astronomers believed hydrogen-dominated atmospheres would be too hot for life. The greenhouse effect should create Venus-like conditions rather than Earth-like ones. Recent modeling has revealed something remarkable, though. Under proper conditions, these hydrogen blankets might actually function as cosmic thermostats, maintaining temperatures allowing liquid oceans underneath. Imagine skies thick with hydrogen, but beneath that alien atmosphere lies an ocean potentially dwarfing all Earth's seas combined. Atmospheric pressure might be dozens of times greater than ours, yet liquid water could flow and possibly harbor life forms beyond our imagination. This represents the world that James Webb Space Telescope has been studying with unprecedented precision, and what it's discovered there has astronomers questioning everything they thought they understood about life's requirements in the universe. When James Webb focused its infrared sensors on K2-18b, it didn't observe the planet directly. Instead, it used transmission spectroscopy, essentially using the host star as a cosmic backlight. As K2-18b passed before its star during what astronomers term a transit, starlight filtered through the planetary atmosphere before reaching our telescopes. Different atmospheric molecules absorbed specific light wavelengths, creating chemical fingerprints revealing atmospheric composition. It's like examining rainbow colors to determine which elements created each shade. But instead of a rainbow, scientists analyzed the invisible infrared spectrum, hunting for molecular signatures that could indicate whether this distant world might harbor life. The findings were remarkable. K2-18b's atmosphere is hydrogen-dominated, as expected for subneptunes. But mixed with that hydrogen are other molecules suggesting this world might be more Earth-like than anyone hoped. Water vapor appears, though in smaller concentrations than initially anticipated. Carbon dioxide and methane exist at approximately 1% atmospheric levels each. Notably, ammonia is scarce, which actually supports the hypothesis that liquid water oceans might exist beneath the hydrogen atmosphere. This chemical mixture precisely matches theoretical Hycean world predictions. Methane and carbon dioxide presence, combined with ammonia shortage, suggests atmospheric chemistry driven by interactions between the thick hydrogen atmosphere and underlying ocean. Here's where the narrative takes a turn that has the entire astronomical community holding its breath. Hidden within spectroscopic data at detectability's edge is a signal that could change everything. A molecular signature that, if confirmed, would represent the strongest extraterrestrial life evidence yet discovered. The molecule in question is dimethyl sulfide, commonly known as DMS. On Earth, this compound has a very specific origin story. It's produced almost exclusively by living organisms, particularly marine phytoplankton floating in our oceans. When you smell that distinctive ocean breeze during a walk along the beach, part of what you're detecting is DMS being released by microscopic life in the water. DMS is what scientists call a biosignature, a chemical that, as far as we know, only biological processes can create. It's not like oxygen, which can be produced by non-biological means. It's not like methane, which can bubble up from geological processes. Dimethyl sulfide, at least on Earth, is the exclusive calling card of life. K2-18b's DMS detection remains preliminary, existing at what scientists call 3 sigma statistical significance. This means approximately 0.3% chance the signal is cosmic noise, a false positive from instrumental limitations or complexities of analyzing light that traveled 124 light-years through space. Reaching the scientific discovery gold standard requires 5 sigma significance, reducing false positive probability to less than 0.00006%. But even at 3 sigma, this detection represents something unprecedented in searching for extraterrestrial life. Never before have we found such a compelling biosignature candidate in another world's atmosphere. Never before have we had a molecule this strongly associated with biological processes detected beyond our solar system. Dr. Niku Madhusudhan from Cambridge University, who led the research team, has emphasized careful boundaries around their claims. "That's not what we're claiming," he told reporters when asked about detecting life. "But in the best-case scenario, it's the potential for life." This measured response reflects modern astronomy's careful nature, where extraordinary claims require extraordinary evidence. K2-18b's DMS detection is extraordinary but not yet definitive. Here's the complication. While DMS is primarily biological on Earth, we can't assume this holds true everywhere in the universe. Recent studies show dimethyl sulfide can be produced through non-biological means. It's been detected in comets, ancient frozen relics from the early solar system where life as we know it cannot exist. Laboratory experiments demonstrate DMS can be synthesized under prebiotic conditions using chemical processes not requiring living organisms. This creates profound challenges for scientists interpreting K2-18b data. The detected DMS atmospheric concentrations are thousands of times higher than Earth's levels. If life produces this molecule on K2-18b, it's doing so at scales and concentrations dwarfing anything in our terrestrial experience. Alternatively, unknown chemical processes might occur in Hycean world exotic environments, producing DMS through purely geological or atmospheric mechanisms. The hydrogen-rich atmosphere combination, potentially vast oceans, and unique chemistry at their interface could create conditions unlike anything on Earth. The uncertainty surrounding DMS detection has created a fascinating astronomical community divide. Some researchers are cautiously optimistic, viewing this as the most promising biosignature detection yet, and calling for additional observations to confirm or refute findings. Others are more skeptical, pointing to marginal statistical significance and possible non-biological explanations. This debate reflects broader astrobiology tension between wanting to find life and maintaining scientific rigor. Discovering extraterrestrial life would be history's most significant finding, fundamentally changing our understanding of our universal place. That very significance means we must be absolutely certain before making such claims. The James Webb Space Telescope represents humanity's most powerful tool for investigating these questions. Its 6.5-meter mirror collects infrared light with unprecedented sensitivity, allowing astronomers to detect molecular signatures in exoplanet atmospheres completely beyond previous instruments' reach. Unlike Hubble Space Telescope, which observes primarily visible light, James Webb was specifically designed to hunt biosignatures in the electromagnetic spectrum's infrared portion. This capability is crucial because many life-associated molecules, including water vapor, carbon dioxide, methane, and potentially DMS, have strongest absorption features at infrared wavelengths. The telescope's ability to achieve precisions better than 1 part in 10,000 during transit observations represents a technological marvel revolutionizing exoplanet science. When K2-18b passes before its host star, tiny starlight fractions filtering through the planet's atmosphere carry chemical composition information. James Webb can detect filtered light variations smaller than perfectly steady LED bulb fluctuations. This extraordinary precision enabled the potential DMS detection initially. The signal is so subtle it exists right at measurement edge for even our most advanced instruments. It's a testament to both James Webb's capabilities and research team's dedication, who spent months carefully analyzing every photon of data. However, precision alone isn't enough to confirm K2-18b life presence. The detection needs repeatability, statistical significance, and a theoretical framework explaining how such high DMS concentrations might be produced and maintained in the planet's atmosphere. This is where future observations become crucial. The research team has identified specific instruments and observation strategies that could elevate DMS detection from its current 3 sigma status to the 5 sigma threshold required for scientific discovery. Additional James Webb observing time using the most sensitive spectrographs could provide definitive answers about whether dimethyl sulfide truly exists in K2-18b's atmosphere. The plan requires between 16 and 24 additional observation hours, a substantial allocation of humanity's most precious scientific resources. The competition for James Webb observing time reflects the telescope's revolutionary impact on multiple astronomy areas. While exoplanet atmospheric characterization represents just one of the instrument's scientific capabilities, potential biosignature detection has generated intense worldwide researcher interest. The telescope schedule is booked months ahead, with hundreds of research teams competing for access to unprecedented capabilities. This scheduling challenge has forced the astronomical community to develop new frameworks for prioritizing observations based on potential scientific impact. Discovering extraterrestrial life would rank among history's most significant achievements. But so would detecting first galaxies formed after the Big Bang or characterizing atmospheres of planets in our own solar system. Committees responsible for allocating telescope time must weigh these competing priorities while ensuring efficient resource use. K2-18b implications extend far beyond a single exoplanet. Subneptunes like K2-18b are among our galaxy's most common planet types, comprising a significant fraction of worlds discovered by planet-hunting missions. If these Hycean worlds can support life, habitable planets might be far more numerous than imagined. Traditional habitable exoplanet searches focused on rocky worlds similar to Earth orbiting sun-like stars at distances where liquid water could exist on surfaces. But Hycean planets expand habitability's definition to include vast populations of previously overlooked worlds. These hydrogen-wrapped ocean worlds could remain habitable even at distances where traditional rocky planets would be frozen solid. The greenhouse effect from thick atmospheres might maintain liquid oceans under conditions impossible for Earth-like worlds. This suggests the habitable zone around every star might be much larger than thought, potentially doubling or tripling the number of worlds where life could exist. K2-18b study is also revealing incredible diversity existing among planetary atmospheres. Each world we examine in detail shows new possibilities for how atmospheric chemistry can work, expanding our understanding of what environments might support life. As we continue peering deeper into cosmos with increasingly sophisticated instruments, we're discovering the universe is far stranger and more varied than our Earth-based perspective ever suggested. K2-18b represents just the beginning of this discovery journey, a world that has already challenged our habitability assumptions and might soon provide answers to one of humanity's most profound questions. The challenges facing K2-18b researchers extend beyond technical difficulties of detecting molecules across interstellar distances. We're essentially trying to understand an entirely alien world using instruments designed based on our understanding of Earth's atmosphere and chemistry. It's like trying to decode a language where we only know a few words and aren't even sure those words mean the same thing in different contexts. Consider the audacity of what we're attempting. We're taking light that left a distant star 124 years ago, light that traveled through space vacuum longer than any human lifespan, and using it to determine whether microscopic organisms might float in an alien ocean beneath a hydrogen sky. The precision required pushes technology to absolute limits. Atmospheric models used to interpret K2-18b's spectroscopic data rely heavily on understanding chemistry and physics as they operate under Earth-like conditions. But Hycean worlds represent environments so exotic that terrestrial experience might inadequately understand them. The pressures, temperatures, and chemical interactions occurring in K2-18b's atmosphere could create entirely new molecular formation and destruction pathways. This uncertainty becomes particularly acute considering the potentially detected dimethyl sulfide concentrations. Dr. Eddie Schwieterman from UC Riverside, who studies biosignatures and atmospheric chemistry, has pointed out that such extreme concentrations raise important viability questions about the life hypothesis. The preliminary data suggests levels thousands of times higher than Earth's atmosphere observations. If life produces these molecules, it would need to do so on scales dwarfing our planet's entire ocean biomass. On Earth, phytoplankton produce DMS in relatively small quantities, and atmospheric chemistry quickly breaks it down. For K2-18b to maintain such high levels, Either production mechanisms would need extraordinary efficiency or destruction pathways would need severe limitation. One possibility is that hydrogen-dominated atmosphere unique chemistry might create conditions where DMS is more stable than in oxygen-rich environments like Earth's. Hydrogen atmospheres lack highly reactive hydroxyl radicals that destroy many organic molecules in our atmosphere, potentially allowing biosignature gases to accumulate at much higher concentrations. Alternatively, the hydrogen-rich environment might enable entirely different biochemical pathways producing DMS through processes we've never encountered on Earth. Life has remarkable ability to adapt to extreme environments, and organisms potentially existing in K2-18b's oceans could have evolved metabolisms unlike anything in our terrestrial experience. The possibility of false positives looms large in K2-18b discussions. Astrobiology history is littered with promising discoveries later explained mundanely. The 1976 Viking missions to Mars detected what appeared to be biological activity in Martian soil samples, generating tremendous excitement before being explained by unexpected soil chemistry. More recently, phosphine detection in Venus's atmosphere sparked speculation about aerial microbes before alternative production mechanisms were proposed. These cautionary tales have shaped the astronomical community's biosignature detection approach, creating healthy skepticism culture demanding multiple evidence lines before accepting extraordinary claims. K2-18b's DMS detection, while intriguing, represents just one piece of what would need to be a much larger puzzle before scientists would comfortably claim life's discovery. Part of the challenge lies in remote sensing's inherent limitations. We can only observe K2-18b during brief moments when it passes before its host star. Even then, we're analyzing incredibly subtle changes in the star's light spectrum. These observations provide planetary atmospheric chemistry snapshots, but they can't tell us about temporal variations, spatial distributions, or underlying processes driving chemical production. On Earth, biosignatures like DMS show complex variation patterns across different seasons, locations, and ecological conditions. Marine phytoplankton blooms create temporary DMS production increases, while ocean temperature and chemistry changes affect the molecule's atmospheric lifetime. We have no way of knowing whether similar variations might occur on K2-18b or how they might affect spectroscopic data interpretation. The research team led by Dr. Madhusudhan has acknowledged these uncertainties while maintaining cautious optimism about their findings. They've outlined specific follow-up observations that could strengthen or refute the DMS detection, including longer exposure times with James Webb's most sensitive instruments and observations at additional wavelengths that could provide independent confirmation of the molecule's presence. These future observations represent a critical test for the biosignature hypothesis. If DMS is indeed present in K2-18b's atmosphere at levels suggested by preliminary data, more extensive observations should detect it with much higher statistical significance. Conversely, if the initial detection was a false positive, additional observations should fail to confirm the molecule's presence. The timeline for these follow-up observations depends on the complex scheduling of James Webb Space Telescope time, allocated through a competitive process involving research teams worldwide. K2-18b represents just one target among hundreds of high-priority objects astronomers want to study with this revolutionary instrument. However, the potential significance of confirming or refuting a biosignature detection makes it likely additional observing time will be allocated to this system. While awaiting crucial follow-up observations, theoretical work continues on understanding how life might operate in Haitian environments. K2-18b conditions would be unlike anything terrestrial organisms experience, requiring life forms adapted to high atmospheric pressures, hydrogen-rich chemistry, and potentially very different ocean compositions than Earth sees. Some researchers have begun exploring whether Earth-based extremophiles, organisms thriving in harsh environments, might provide clues about life types that could exist on Haitian worlds. Deep-sea bacteria living near hydrothermal vents, microorganisms surviving in highly acidic or alkaline conditions, and archaea thriving in high-pressure environments all demonstrate life's remarkable ability to adapt to conditions lethal to most organisms. Laboratory experiments are being designed to test whether terrestrial microorganisms could survive and reproduce under conditions similar to those expected on K2-18b. These studies involve exposing bacteria and archaea to hydrogen-rich atmospheres, high pressures, and altered ocean chemistry to see if any Earth-based life forms might provide analogs for potential Haitian organisms. The results of these experiments could inform our interpretation of K2-18b observations by providing insights into the kinds of metabolisms and biochemical pathways that might be possible under Haitian conditions. If terrestrial organisms can adapt to hydrogen-rich environments and produce molecules like DMS under those conditions, it would strengthen the biological interpretation of spectroscopic data. The broader implications of discovering K2-18b life extend far beyond astrobiology into fundamental questions about life's nature and distribution in the universe. For decades, extraterrestrial life search has been guided by following the water principle, looking for worlds where liquid water might exist on planetary surfaces. Discovering potentially habitable Haitian worlds would represent a paradigm shift in this approach. If life can indeed thrive in sub-Neptune planets' hydrogen-wrapped oceans, then potentially habitable worlds in our galaxy could increase by orders of magnitude. Subneptunes are among the most common exoplanet types, and red dwarf stars like K2-18b's host are the Milky Way's most numerous stellar types. Abundant planets and abundant stars combination could mean Haitian worlds represent the galaxy's most common habitable environment. This possibility has profound Drake equation implications, the famous formula used to estimate communicating civilizations in our galaxy. If Haitian worlds can support life, and if that life can evolve to intelligence and technology, then the universe might be far more populated than our Earth-centric perspective suggested. K2-18b life detection would also raise immediate questions about whether similar biosignatures might be detectable on other sub-Neptune exoplanets. Astronomers have already identified dozens of other sub-Neptunes orbiting in their stars' habitable zones, many suitable targets for biosignature searches with James Webb and future telescopes. The prospect of finding life signatures on multiple worlds would transform astrobiology from a field focused on detecting life to one concerned with understanding life's diversity and distribution throughout the cosmos. Each world would likely host unique ecosystems adapted to their specific atmospheric and oceanic conditions, creating vast biological diversity tapestries we're only beginning to imagine. Yet even contemplating these extraordinary possibilities, the scientific community maintains commitment to rigorous analysis and evidence-based conclusions. K2-18b's potential DMS detection represents our most promising extraterrestrial life search lead, but it remains just that, a lead requiring careful investigation and confirmation. The next few years will be crucial for determining whether K2-18b truly hosts biosignatures indicating life or whether these signals represent previously unknown chemical processes in exotic atmospheric environments. Either outcome would advance our planetary atmosphere's understanding and life's potential in the universe. But only one would answer the ancient question that has driven human curiosity since we first looked at stars and wondered if we were alone. As James Webb continues observations and theoretical models become more sophisticated, we edge closer to answers that could fundamentally change our cosmic place understanding. K2-18b has already shown us the universe is stranger and more diverse than imagined, and it may yet reveal whether that strangeness includes life's familiar chemistry itself. The story of how we arrived at this momentous discovery is as fascinating as the discovery itself. When James Webb Space Telescope first locked onto K2-18b, astronomers weren't expecting to stumble upon what might be history's most significant finding. They were simply conducting routine atmospheric characterization of an interesting subneptune, part of a broader survey to understand how these common yet mysterious worlds differ from planets in our own solar system. The observations themselves required extraordinary patience and precision. Unlike photographing a distant galaxy or nebula, studying an exoplanet's atmosphere demands perfect timing. Scientists had to wait for K2-18b to pass directly between its host star and Earth, an event called a transit that occurs only once every 33 days. Even then, the window of opportunity lasts mere hours as the planet crosses the star's face. During those precious moments, James Webb collected photons that had traveled 124 light-years through the cosmos, light that had been filtered through K2-18b's atmosphere and carried within it the chemical signatures of that distant world. The data arrived as streams of numbers, wavelengths, and intensities that meant nothing to casual observers, but contained secrets that would keep atmospheric chemists busy for months. Dr. Madhusudhan's team spent countless hours parsing through this data, looking for telltale absorption lines that would reveal which molecules existed in K2-18b's atmosphere. Each molecule has its own unique fingerprint in the infrared spectrum, like a cosmic barcode identifying its presence. Water vapor shows up at specific wavelengths, carbon dioxide at others, and methane creates its own distinctive pattern of absorption lines. The initial results were encouraging but not revolutionary. Water vapor detection, while exciting, had been anticipated based on theoretical Hessian world models. Carbon dioxide and methane presence fitted neatly into expectations for this planet type. Ammonia shortage was actually good news, supporting the hypothesis that liquid oceans might exist beneath the hydrogen atmosphere. But then something unexpected appeared in the data. Hidden among the forest of absorption lines was a signal that didn't belong to any of the molecules they'd been expecting to find. At first, researchers thought it might be an instrumental artifact or contamination from Earth's own atmosphere. Space-based telescopes can sometimes pick up trace amounts of terrestrial gases that cling to spacecraft or outgas from its components. Yet as they dug deeper into the analysis, cross-referencing multiple observations and eliminating potential error sources, the signal persisted. The wavelengths matched those expected for dimethyl sulfide. But the implications were so profound that the team spent months double and triple checking their work before even considering publication. The peer review process added another scrutiny layer to the findings. Independent researchers examined data analysis methods, questioned statistical techniques, and proposed alternative explanations for observed signals. This rigorous vetting process, while sometimes frustrating for scientists eager to share discoveries, represents one of modern science's greatest strengths. Some reviewers suggested the DMS signal might be contamination from other molecules with similar spectroscopic features. Others questioned whether statistical significance was sufficient to support such an extraordinary claim. The research team addressed each concern methodically, refining their analysis and acknowledging uncertainties that remained. Their findings' publication in a major astronomical journal marked the beginning rather than the end of the scientific process. Within days, research groups worldwide began their own independent analyses of publicly available data. Some confirmed the team's findings, while others expressed skepticism about spectroscopic signal interpretation. This healthy scientific debate reflects the magnitude of what's at stake. Detecting a genuine biosignature would represent the most significant discovery in science history, fundamentally altering our understanding of life's prevalence in the universe. Such extraordinary claims naturally invite extraordinary scrutiny, and the scientific community has responded with appropriate caution and rigor. Meanwhile, theoretical work has begun exploring what life might actually look like on a world like K2-18b. The conditions there would be unlike anything in Earth's biosphere, presenting unique challenges and opportunities for any organisms that might call that world home. The atmospheric pressure at the ocean surface could be dozens of times greater than at Earth's sea level, creating an environment more similar to our deep ocean trenches than our familiar surface waters. The chemistry of a hydrogen-rich atmosphere would fundamentally alter the kinds of biochemical reactions that could occur. On Earth, oxygen plays crucial roles in many biological processes, from respiration to forming complex organic molecules. In K2-18b's hydrogen-dominated environment, life would need to find alternative pathways for energy production and molecular construction. Some researchers have proposed that life in such environments might actually have advantages over terrestrial organisms. The absence of highly reactive oxygen species could reduce cellular damage and potentially extend organism lifespans. High atmospheric pressure might enable more efficient gas exchange between organisms and their environments. The vast oceans could provide enormous habitat space volumes, potentially supporting ecosystems of unimaginable scale and diversity. The potential DMS detection on K2-18b has also sparked renewed interest in understanding how this molecule behaves under exotic conditions. Laboratory experiments are being designed to test whether DMS can be produced through non-biological processes under high-pressure, hydrogen-rich conditions that might exist on Hycean worlds. These experiments involve recreating K2-18b's atmosphere extreme conditions in specialized chambers, then exposing various chemical mixtures to see if DMS can form without biological intervention. The results could either strengthen the case for life by ruling out abiotic production pathways or provide alternative explanations for observed signals. Simultaneously, computational models are being developed to simulate the complex chemistry that might occur in K2-18b's atmosphere and oceans. These models attempt to account for unique interactions between hydrogen-rich atmospheres and liquid water, exploring how molecules might form, react, and accumulate under conditions never before encountered in our solar system. The challenges facing these theoretical efforts are immense. We're essentially trying to predict chemistry behavior under conditions so extreme and exotic that we have no direct experience with them. It's like trying to understand game rules we've never played, using equipment we've never seen in an environment we've never visited. Yet these efforts are crucial for interpreting K2-18b observational data. Without theoretical frameworks to guide our understanding, we're left with intriguing signals but no way to determine their significance. The interplay between observation and theory will ultimately determine whether we're looking at life evidence or simply exotic atmospheric chemistry signatures. The technological requirements for studying worlds like K2-18b have pushed instrument development to new extremes. Precision needed to detect potential biosignatures across interstellar distances requires spectrographs measuring wavelengths to parts per billion accuracies. Stability needed to track subtle changes over multiple observations demands thermal control systems maintaining temperatures to within millikelvin. James Webb represents current technology pinnacle, but even it struggles at edges of what's needed for definitive biosignature detection. Future space telescopes are already being designed with even greater sensitivity and precision, instruments that could potentially detect biosignatures with statistical confidence needed for scientific certainty. The extremely large telescopes currently under construction on Earth will complement space-based observations with their own unique capabilities. Their enormous mirrors will collect vast light amounts, enabling detailed exoplanet atmosphere spectroscopic studies with unprecedented resolution. Space-based and ground-based observation combinations could provide multiple evidence lines needed to confirm or refute potential biosignature detections. As we stand at this extraordinary crossroads in human history, the implications extend far beyond astronomy and astrobiology. Discovering life beyond Earth would fundamentally alter philosophy, religion, and our understanding of our place in the cosmic order. It would raise immediate questions about that life's nature, its origins, and its relationship to terrestrial biology. Would K2-18b life share common ancestry with Earth's organisms, suggesting life might have spread between worlds through some cosmic seeding process? Or would it represent an entirely independent genesis, proving life is a natural consequence of chemistry under right conditions? These questions would drive scientific inquiry for generations to come. K2-18b life detection would also have profound implications for searching for intelligent life in the universe. If simple organisms can thrive in Hycean world's exotic environments, what might be possible given millions or billions of years of evolution? Could intelligence emerge from such alien biospheres, leading to technological civilizations unlike anything we might imagine? These considerations have led some researchers to propose that we should be listening for signals from Hycean worlds, not just Earth-like planets. The SETI Institute and other organizations dedicated to searching for extraterrestrial intelligence are beginning to consider how their search strategies might need to evolve if life proves common on sub-Neptune exoplanets. The possibility of communicating with K2-18b life, however, faces enormous practical challenges. The 124 light-year distance means any signal would take nearly 250 years to make a round trip. Even if intelligent life existed on K2-18b and was actively trying to communicate with us, the conversation would unfold on timescales dwarfing human civilization. Yet merely knowing that life existed elsewhere would transform our species' perspective on existence itself. We would no longer be alone in the universe, no longer unique in our ability to contemplate the cosmos and our place within it. The implications would ripple through every aspect of human culture and understanding. Religious traditions would grapple with expanding their cosmologies to include life beyond Earth. Philosophers would debate what the discovery meant for concepts of purpose and meaning in the universe. Artists and writers would find new inspiration in imagining alien life possibilities and alternative biospheres. Education systems would need to incorporate astrobiology into their curricula, preparing future generations to live in a universe known to harbor life beyond Earth. The discovery would likely inspire unprecedented investment in space science and exploration, as humanity sought to learn more about our cosmic neighbors and perhaps even develop technologies for interstellar travel. The economic implications would be substantial as well. The space industry would experience explosive growth as governments and private organizations invested in telescopes, spacecraft, and technologies needed to study distant worlds. New research fields would emerge, creating career opportunities for scientists, engineers, and technicians specializing in astrobiology and exoplanet science. But perhaps most profoundly, discovering life on K2-18b would serve as a reminder of how much we still don't know about the universe we inhabit. Each answer we uncover seems to reveal 10 new questions, expanding rather than limiting cosmic mystery's scope. As we await future observation results that will either confirm or refute the potential K2-18b biosignature, we find ourselves balanced on the edge of what might be history's greatest discovery. The next few years could bring us face to face with the reality that we share this universe with other life forms, fundamentally altering our understanding of what it means to be alive in this vast cosmos. The gentle light from K2-18b's host star continues its journey toward Earth, carrying within it distant world secrets that might harbor life. Each photon reaching our telescopes brings us closer to answering the question that has haunted humanity since we first looked up at the night sky and wondered if we were truly alone among the stars. The journey toward understanding K2-18b's life potential has revealed just how much we're pushing scientifically possible boundaries with current technology. When astronomers first began analyzing spectroscopic data from this distant world, they quickly realized they were venturing into uncharted territory. The molecules they were hunting for existed at concentrations so low that detecting them was like trying to identify a whisper in a thunderstorm. The precision required for these measurements is almost incomprehensible. Imagine trying to measure human hair thickness from a football field's distance, and you begin to appreciate technical challenges facing K2-18b researchers. The variations in starlight that carry planetary atmospheric composition information represent changes of just a few parts per million in the host star's overall brightness. This extraordinary precision is possible only because of revolutionary infrared detector technology advances and data processing algorithms. James Webb sensors are cooled to temperatures just a few degrees above absolute zero, reducing thermal noise to levels impossible to achieve with earlier space telescope generations. Data processing systems can identify and correct for subtle systematic errors that would completely overwhelm tiny signals from distant exoplanet atmospheres. Yet, even with these technological marvels, K2-18b potential biosignature detection required months of painstaking analysis. Research teams had to account for everything from cosmic ray hits on detectors to minute variations in telescope pointing stability. Each potential error source had to be identified, modeled, and removed from data before true atmospheric signals could emerge. The complexity of this process becomes even more daunting when considering we're trying to understand an atmosphere unlike anything in our own solar system. Chemical interactions occurring in K2-18b's hydrogen-rich environment might follow pathways never studied in terrestrial laboratories. Pressure and temperature conditions could enable molecular formations impossible under Earth-like conditions. The researchers studying K2-18b find themselves in a peculiar position, simultaneously hopeful and skeptical about their own findings. They've spent years developing the expertise needed to extract meaningful signals from the noise of interstellar observations. Yet, they're the first to acknowledge the limitations and uncertainties in their data. This intellectual honesty reflects the best traditions of scientific inquiry where researchers must balance enthusiasm for discovery with rigorous self-criticism. The pressure surrounding K2-18b research extends beyond normal academic scrutiny. The potential for discovering life beyond Earth has captured public imagination in ways that more routine astronomical discoveries cannot match. Media outlets worldwide have covered the story, often with headlines that strain the boundaries between responsible reporting and sensationalism. The researchers find themselves navigating not just scientific challenges but also the complex dynamics of public communication and expectation management. This public attention, while sometimes uncomfortable for scientists accustomed to working in relative obscurity, serves an important purpose in advancing our understanding of the cosmos. The excitement generated by potential signature detections helps justify the enormous public investments in space, telescopes, and astronomical research. It reminds us why we build billion-dollar instruments and point them at distant worlds searching for answers to questions that define our place in the universe. The K2-18b observations have also revealed the incredible sophistication required for modern astronomical research. the data analysis pipelines used to process James Webb observations, represent some of the most advanced signal processing techniques ever developed. These systems must account for everything from minute thermal variations in the telescope structure to the subtle effects of cosmic radiation on the detectors. Each observation of K218b generates terabytes of data that must be carefully calibrated, processed, and analyzed before meaningful scientific conclusions can be drawn. The raw data bears little resemblance to the elegant spectroscopic plots that appear in research papers. Instead, it consists of millions of individual measurements, each carrying a tiny piece of information about the distant worlds.
Atmosphérique composition.
The transformation of this raw data into scientific knowledge requires expertise spanning multiple disciplines. Instrument specialists understand how the telescope's various components affect the collected light. Atmospheric physicists model how different molecules absorb infrared radiation. Statisticians develop methods for extracting meaningful signals from noisy data. Computer scientists create algorithms capable of processing vast data sets efficiently. This collaborative effort reflects the increasing complexity of modern astronomy, where individual researchers must rely on teams of specialists to tackle questions that would have been impossible to address just decades ago. The detection of potential biosignatures on distant exoplanets represents perhaps the ultimate expression of this collaborative approach, requiring humanity's most advanced technologies and our deepest understanding of physics, chemistry, and biology. The implications of the K218b research extend far beyond the specific question of whether life exists on this particular world. The techniques developed for analyzing its atmosphere are being applied to dozens of other potentially habitable exoplanets, creating an unprecedented survey of atmospheric diversity among worlds that might support life. Each new observation adds to our understanding of how planetary atmospheres evolve and what conditions might be necessary for biological processes to emerge and persist. The growing catalog of exoplanet atmospheric compositions is revealing patterns that could help us understand the fundamental requirements for habitability. Some worlds show clear evidence of water vapor, while others appear dry despite orbiting in their stars' habitable zones. The differences might reflect varying formation histories, different stellar environments, or simply the natural diversity that emerges from the complex processes of planetary evolution. This comparative approach to exoplanet science mirrors the methods that revolutionized our understanding of planetary formation within our own solar system. By studying the diverse worlds orbiting our Sun, from the hellish surface of Venus to the methane lakes of Titan, scientists develop theories that could explain how planets form and evolve under different conditions. The extension of this approach to exoplanets is providing insights into planetary processes operating on scales and under conditions impossible to study within our local cosmic neighborhood. The search for biosignatures on K218b and similar worlds is also driving advances in laboratory science that have applications far beyond astronomy. Understanding how molecules behave under the extreme conditions found on hellish worlds requires experimental techniques that push the boundaries of high-pressure chemistry and physics. The results of these experiments inform not just our interpretation of exoplanet observations, but also our understanding of fundamental chemical processes under conditions that might exist deep within planetary interiors. Some of the most intriguing aspects of K218b's atmospheric chemistry involve reactions that simply cannot occur under Earth-like conditions. The combination of high pressures, hydrogen-rich chemistry, and potentially exotic ocean compositions could enable molecular processes that have never been observed in terrestrial laboratories. Understanding these processes requires developing new experimental techniques and theoretical frameworks that expand our basic knowledge of chemistry and physics. The potential biological implications of these exotic chemical processes are particularly fascinating. Life on Earth has evolved to exploit the specific chemical and physical conditions found in our planet's biosphere, but the fundamental principles of biology might operate very differently under the conditions found on heightened worlds. The high atmospheric pressures could enable biological processes that would be impossible under Earth-like conditions, while the hydrogen-rich chemistry could provide energy sources unavailable to terrestrial organisms. Researchers studying extremophile on Earth have discovered organisms that thrive under conditions once thought incompatible with life. Bacteria living in highly acidic hot springs are thriving in salt concentrations that would be lethal to most organisms, and microbes surviving in the high-pressure environments of deep ocean trenches all demonstrate life's remarkable ability to adapt to extreme conditions. These discoveries provide hints about what might be possible in the even more extreme environments of distant exoplanets. The study of terrestrial extremophiles has become crucial for interpreting potential biosignature detections on worlds like K218b. If Earth-based organisms can survive and reproduce under conditions similar to those found on high-end worlds, it strengthens the case that life might indeed be possible on these distant planets. Conversely, if no terrestrial organisms can tolerate Hyson-like conditions, it suggests that any life on such worlds would need to be fundamentally different from anything in Earth's biosphere. Laboratory experiments designed to test the limits of terrestrial life under Hyson conditions are yielding surprising results. Some microorganisms show remarkable resilience when exposed to high-pressure hydrogen atmospheres, maintaining metabolic activity under conditions that would quickly kill most familiar organisms. These findings suggest that the boundary between habitable and uninhabitable conditions might be more flexible than previously thought. The implications extend beyond individual organisms to entire ecosystem dynamics. If life can indeed thrive under Hyson conditions, the resulting ecosystems might operate according to principles very different from those governing Earth's biosphere. The energy sources, nutrient cycles, and evolutionary pressures would all be alien to our terrestrial experience, potentially leading to forms of biological organization unlike anything we've encountered. The possibility of discovering such alien ecosystems raises profound questions about our methods for detecting and characterizing life beyond Earth. Current biosignature research focuses primarily on molecules and processes familiar from terrestrial biology. But truly alien life might produce chemical signatures that we wouldn't recognize as biological. The challenge becomes not just detecting life, but recognizing it when it operates according to principles we've never encountered. This recognition problem becomes particularly acute when considering the potential for false negatives in biosignature searches. While much attention focuses on false positives, situations where natural processes mimic biological signatures, the opposite scenario might be equally problematic. If alien life produces Signatures unlike anything in our terrestrial experience, we might overlook genuine evidence of biological activity simply because it doesn't match our expectations. The K2-18b observations have highlighted this challenge by revealing atmospheric chemistry that doesn't fit neatly into either biological or non-biological categories. The unusual concentrations and combinations of molecules detected in the planet's atmosphere could represent either exotic life forms or previously unknown atmospheric processes. Distinguishing between these possibilities requires expanding our theoretical frameworks to encompass phenomena beyond our current understanding. This expansion of scientific understanding represents one of the most exciting aspects of exoplanet research. Each new world we study reveals possibilities we hadn't previously considered, forcing us to question assumptions and develop new theories to explain observations that don't fit existing models. The process mirrors the great revolutions in scientific thinking that have periodically transformed our understanding of the natural world. The study of K2-18b is also revealing the importance of long-term monitoring in understanding exoplanet atmospheres. Unlike the static chemical compositions we might assume from single observations, planetary atmospheres are dynamic systems that can change dramatically over time. Weather patterns, seasonal variations, and geological activity all influence atmospheric chemistry in ways that single transit observations might miss. The brief glimpses we get of exoplanet atmospheres during transit events provide snapshots of complex evolving systems. Understanding whether observed chemical signatures represent stable atmospheric conditions or temporary phenomena requires multiple observations spread across months or years. This temporal aspect of atmospheric characterization adds another layer of complexity to interpreting potential signature detections. Future observations of K2-18b will need to address these temporal questions while also improving the statistical significance of potential biosignature detections. The observing strategies being developed for follow-up studies represent careful compromises between the desire for immediate answers and the need for comprehensive characterization. Each observation requires precious telescope time that could be used to study other potentially habitable worlds, forcing researchers to balance breadth and depth in their investigation strategies. The scheduling challenges facing K2-18b research reflect broader issues in modern astronomy where demand for advanced telescope time far exceeds availability. The James Webb Space Telescope receives observation proposals requesting many times more hours than the instrument can provide, forcing review committees to make difficult decisions about which projects deserve priority. The potential significance of biosignature detections gives K2-18b researchers strong claims on telescope time, but it must compete with other groundbreaking research across all areas of astronomy and astrophysics. This competition for observational resources has fostered innovation in observation planning and data analysis techniques. Researchers are developing methods to extract maximum information from limited observing time using advanced statistical techniques and machine learning algorithms to squeeze every possible insight from hard-won observations. The constraints imposed by telescope scheduling have paradoxically accelerated advances in data analysis that benefit all areas of astronomical research. The technological demands of studying worlds like K2-18b are also driving the development of next-generation space telescopes specifically designed for exoplanet characterization. These future instruments will address many of the limitations that currently constrain biosignature searches, providing the sensitivity and stability needed for definitive detections of life beyond Earth. The Nancy Grace Roman Space Telescope, scheduled for launch in the coming years, will complement James Webb with capabilities optimized for different aspects of exoplanet research. While James Webb excels at detailed atmospheric characterization of known exoplanets, Roman will survey vast areas of sky to discover new worlds and identify the most promising targets for follow-up studies. The synergy between these instruments could revolutionize our ability to find and characterize potentially habitable worlds. Ground-based telescopes are also evolving to meet the challenges of exoplanet atmospheric studies. The extremely large telescopes currently under construction will provide unprecedented light-gathering power and resolution, enabling detailed spectroscopic studies that complement space-based observations. The combination of space and ground-based capabilities could provide the multiple lines of evidence needed to definitively confirm biosignature detections. These technological advances represent massive investments by the international scientific community in answering fundamental questions about life in the universe. Government space agencies, international collaborations, and private organizations are dedicating billions of dollars to building the tools needed to detect and characterize life on distant worlds. The investments reflect not just scientific curiosity, but recognition that such discoveries could fundamentally transform our understanding of our place in the cosmos. The potential return on these investments extends far beyond astronomy into areas that could benefit all of human society. The technologies developed for detecting trace gases in exoplanet atmospheres have applications in environmental monitoring, medical diagnostics, and industrial process control. The data analysis techniques pioneered for astronomical research are finding uses in fields ranging from finance to healthcare. The international collaborations fostered by major space missions create relationships that facilitate cooperation on other global challenges. Yet the ultimate value of discovering life beyond Earth cannot be measured in technological spin-offs or economic benefits. Such a discovery would represent a fundamental expansion of human knowledge that would influence how we understand ourselves and our relationship to the universe. The psychological and philosophical implications would ripple through every aspect of human culture, from science and religion to art and literature. The ongoing research into K218b's potential biosignatures continues to generate both excitement and controversy within the scientific community. Each new analysis of the available data seems to reveal additional complexity rather than providing definitive answers. The atmosphere of this distant world appears to be far more intricate than initial observations suggested, with chemical processes that don't fit neatly into existing theoretical frameworks. The complexity itself might be the most important discovery emerging from K218b research. The assumption that exoplanet atmospheres would be relatively simple systems governed by well-understood physics and chemistry is proving naive, as observations reveal the incredible diversity and sophistication of atmospheric processes operating on distant worlds. Each new detection challenges our theoretical models and forces us to expand our understanding of what's possible in planetary atmospheric chemistry. This expansion of knowledge represents the essence of scientific discovery, the gradual push against the boundaries of human understanding that has driven progress throughout history. Whether K218b ultimately proves to harbor life or simply represents an exotic example of atmospheric chemistry. The research has already advanced our knowledge in ways that will influence science for generations to come. The techniques developed, the theoretical frameworks expanded, and the questions raised will guide future investigations into the cosmic prevalence of life and the incredible diversity of worlds that populate our galaxy. As we await the results of future observations that may finally resolve the mystery of K218b's atmospheric chemistry, we find ourselves participants in one of humanity's greatest adventures. The search for life beyond Earth represents the culmination of centuries of scientific advancement and the beginning of what might be an even more extraordinary chapter in human understanding. In the quiet spaces between observations, as our most sophisticated instruments continue their patient watch over the cosmos, we balance on the threshold of discoveries that could transform everything we thought we knew about life's place in the universe. The statistical dance between certainty and possibility continues to unfold in laboratories and observatories around the world, where teams of researchers are conducting some of the most sophisticated analyses ever attempted in astronomy. The 3 sigma detection of dimethyl sulfide on K218b represents more than just a number on a statistical chart. It embodies the razor's edge between revolutionary discovery and scientific caution, between the extraordinary and the merely unusual. Consider what 3 sigma actually means. In practical terms, if you were to repeat the same observation 1,000 times under identical conditions, you would expect to see a false positive signal only 3 times. In most fields of science, this level of confidence would be considered rock solid, sufficient to publish results and move forward with additional research. But when the implications are as profound as the discovery of life beyond Earth, the scientific community demands an even higher standard. The 5 sigma threshold that researchers are striving to reach would reduce the probability of a false positive to less than 1 in 3 million. It's the same standard that particle physicists demanded before announcing the discovery of the Higgs boson. Recognizing that extraordinary claims require extraordinary evidence, the question facing K218b researchers is whether they can accumulate enough observational data to cross this statistical finish line. The path toward 5 sigma confidence requires more than simply pointing telescopes at K218b for longer periods. The researchers must also contend with systematic errors, instrumental artifacts, and the inherent limitations of studying a world that exists at the very edge of our technological capabilities. Each additional observation must be carefully planned to maximize the scientific return while minimizing the potential for contamination or misinterpretation. Dr. Madhusudan's team has outlined a specific roadmap for achieving this higher level of statistical confidence. They've identified particular wavelength ranges where the DMS signature should be strongest, instruments that provide the best sensitivity for detecting this molecule, and observational strategies that could eliminate alternative explanations for the observed signals. The plan requires between 16 and 24 hours of additional James Webb observations, a substantial allocation of one of humanity's most precious scientific resources. The competition for James Webb observing time reflects the telescope's revolutionary impact on multiple areas of astronomy, while exoplanet atmospheric characterization represents just one of the instrument's scientific capabilities. The potential for detecting biosignatures has generated intense interest from researchers worldwide. The telescope's Schedule is booked months in advance with hundreds of research teams competing for access to its unprecedented capabilities. This scheduling challenge has forced the astronomical community to develop new frameworks for prioritizing observations based on their potential scientific impact. Discovering life beyond Earth would rank among the most significant achievements in human history. But so, would detecting the first galaxies formed after the Big Bang or characterizing the atmospheres of planets in our own solar system. The committees responsible for allocating telescope time must weigh these competing priorities while ensuring that resources are used efficiently. The international nature of James Webb operations adds another layer of complexity to observation planning. The telescope was built through a partnership between NASA, the European Space Agency, and the Canadian Space Agency, with each organization contributing expertise, funding, and guaranteed observing time, coordinating observations across multiple time zones. And organizational structures requires careful planning and diplomatic skill that rivals the technical challenges of operating the instrument itself. Yet the potential rewards of confirming biosignatures on K2-18 be justified the enormous effort being invested in these than just the discovery of life beyond Earth. Observations. The detection would represent more. It would validate an entirely new approach to searching for habitable worlds, one that expands the definition of habitability far beyond the traditional focus on Earth-like planets orbiting Sun-like stars. The implications for astrobiology would be transformative. If life can thrive in the hydrogen-wrapped oceans of high-end worlds, then the number of potentially habitable planets in our galaxy could increase by orders of magnitude. Sub-Neptune planets like K2-18b are among the most common types of worlds discovered by planet hunting missions, and red dwarf stars like its host are the most numerous stellar types in the Milky Way. The combination suggests that habitable environments might be far more prevalent than our Earth-centric perspective has led us to believe. This statistical revolution in habitability estimates would have profound implications for the famous Drake equation, the framework that astronomers use to estimate the number of communicating civilizations in our galaxy. If worlds can support life, and if that life can evolve toward intelligence and technology, then the universe might be far more populated than we've dared to imagine. The silence we've encountered in our searches for extraterrestrial intelligence might reflect limitations in our search strategies rather than the absence of technological civilizations. The possibility of widespread life in high-end environments is already influencing how researchers approach the search for technosignatures observable evidence of alien technology. Traditional SETI efforts have focused on radio signals from civilizations presumed to be similar to our own, but the discovery of potentially habitable planets suggests that technological species might develop under conditions radically different from those on Earth. Civilizations that evolved in the high-pressure, hydrogen-rich environments of Haitian worlds might develop technologies that operate according to principles unfamiliar to us. Their methods of communication, energy production, and space travel could be so different from our own that we might not recognize them as artificial. This recognition problem poses fundamental challenges for technosignature research that extend far beyond traditional radio astronomy. The search for artificial signals from K2-18b itself presents unique challenges. The 124 light-year distance means that any communication would require nearly 2.5 centuries for a round trip, making real-time conversation impossible across human timescales. Even if intelligent life existed on the planet and was actively trying to communicate with us, the dialogue would unfold across time periods that exceed the lifespan of entire civilizations. Yet the mere knowledge that life existed on K218b would fundamentally alter our species' relationship with the cosmos. We would no longer be alone in the universe, no longer unique in our capacity for consciousness and technological development. The psychological impact would rival the Copernican revolution that displaced Earth from the center of the universe, forcing humanity to reconceptualize our place in the cosmic order. The cultural implications would be equally profound. Religious traditions would grapple with expanding their cosmologies to include life that developed under conditions unlike anything described in their foundational texts. Philosophers would debate whether consciousness and intelligence represent inevitable outcomes of cosmic evolution, or remarkable accidents that occur only under specific circumstances. Artists and writers would find inspiration in imagining the possibilities of life forms adapted to environments beyond our terrestrial experience. Educational systems would face the challenge of preparing students for a universe known to harbor multiple forms of life. The discovery would likely inspire unprecedented investment in science education, as societies recognized the need for citizens capable of understanding and contributing to humanity's expanded cosmic perspective. New fields of study would emerge, combining astrobiology, comparative planetology, and xenophysiology in ways that don't currently exist. The economic implications would be substantial as, well, the space industry would experience explosive growth as governments and private organizations invested in telescopes, spacecraft, and technologies needed to study other, potentially inhabited worlds. The confirmation of life on K218b would transform astrobiology from a speculative field into a practical science with immediate applications for understanding and potentially communicating with alien life forms. Research and development programs would focus on developing technologies for detailed study of distant biospheres, potentially including interstellar missions to nearby habitable worlds. While the enormous distances involved would make such missions extraordinarily challenging, the knowledge that life existed on accessible targets would justify investments in revolutionary propulsion technologies and autonomous spacecraft systems. The biotechnology industry would also experience transformation as researchers sought to understand how life might operate under conditions radically different from those on Earth. The study of extremophiles would expand to include laboratory simulations of Haitian environments potentially, revealing new biochemical pathways and molecular processes with applications in medicine, agriculture, and industrial biotechnology. Yet perhaps the most significant impact would be on human consciousness itself. The confirmation of life on K28b would serve as a cosmic mirror, reflecting back to us the remarkable nature of our own existence while simultaneously demonstrating that life is not unique to our small corner of the universe. The discovery would be both humbling and inspiring, reminding us of our cosmic insignificance while celebrating the extraordinary phenomenon of life itself. The ongoing analysis of K218b's atmospheric data continues to reveal new layers of complexity that challenge our understanding of planetary atmospheric chemistry. Each enhancement of analytical methodologies appears to reveal new molecular compounds and chemical interactions that defy current theoretical classifications. The planet's atmosphere is turning out to be a far more dynamic and intricate system than early measurements had implied. Recent reinterpretations of the spectroscopic datasets have unveiled possible traces of additional organic molecules beyond the much-publicized detection of DMS. Small quantities of complex hydrocarbons, sulfur-based substances, and nitrogen-bearing molecules together depict a form of atmospheric chemistry as intricate as Earth's biosphere. Whether these materials stem from biological activity or unusual abiotic reactions remains an unresolved mystery that continues to fuel scientific investigation. The isotopic ratios found within different atmospheric components offer another promising route for decoding K218b's chemical and potential biological processes. On Earth, life tends to favor lighter isotopes, leaving behind distinctive isotopic fingerprints detectable in air samples. A similar type of isotopic fractionation on K218b could point toward living processes, though understanding such evidence depends heavily on knowing how isotope behavior might differ under its extreme conditions. This type of isotopic analysis becomes even more daunting when performed through spectroscopic observations spanning interstellar distances. The level of precision needed to identify isotopic shifts in exoplanetary atmospheres already stretches modern instruments to their technological limits. Next-generation space observatories will require even higher sensitivity and resolving power to routinely achieve such detailed measurements of faraway worlds. The time-dependent behavior of K218b's atmosphere adds yet another layer of complexity to its interpretation. Because the planet completes an orbit roughly every 33 days, atmospheric conditions could change significantly depending on its position relative to the host star. If seasonal cycles exist, they might alter chemical formation and destruction rates, complicating how scientists interpret individual transit observations. To accurately understand these time-based variations, multiple measurements must be conducted throughout the entire orbital period and possibly across several years. Such long-term monitoring projects demand major allocations of telescope resources, but could yield critical insights into the durability and persistence of potential biosignature compounds in the planet's air. In fact, observing fluctuating atmospheric signals over time could strengthen the argument for biological processes, since living systems often produce cyclic chemical patterns. The three-dimensional organization of K218b's atmosphere marks another major challenge in understanding this remote planet. Present-day observations offer only disk-average data collected during transits, yet the true atmospheric makeup likely varies dramatically with altitude, latitude, and local meteorological dynamics. Future observational methods could make it possible to map these spatial differences, painting a far more detailed picture of its chemical and structural properties. Meanwhile, advanced atmospheric simulations are beginning to examine how circulatory patterns might shape the presence and behavior of possible biosignature molecules. Given the planet's dense hydrogen envelope, intricate wind and circulation systems may be driven by stellar heating and planetary rotation. These global air currents could redistribute chemical elements, producing detectable variations in atmospheric makeup if instruments are sufficiently refined. The magnetic environment of K218b remains poorly understood, but could be a decisive factor in shielding any potential biosphere from intense stellar radiation. Red dwarf stars are notorious for violent flare activity, capable of stripping away atmospheres over geological timescales unless protected by strong planetary magnetic fields. The very persistence of complex atmospheric chemistry on K218b might indirectly indicate the presence of magnetic shielding. Models of magnetic field generation in sub-Neptune-type planets suggest that such worlds could indeed produce powerful magnetospheres if their interiors harbor electrically conductive materials. The unusual forms of water ice thought to exist under the immense internal pressures of K218b might exhibit electrical properties unlike ordinary ice, potentially enabling unique magnetic dynamo mechanisms unseen within our solar system. Interactions between K218b's magnetic field and its hydrogen-dominated atmosphere might create distinctive chemical conditions not found elsewhere in our cosmic vicinity. Charged particles spiraling along magnetic field lines could trigger chemical pathways that synthesize or decompose biosignature molecules through mechanisms unfamiliar to terrestrial laboratories. Grasping these interactions is essential to distinguish biological phenomena from purely physical or chemical explanations of atmospheric complexity. Meanwhile, the search for additional Hyson-class worlds within the K218 system has intensified, as astronomers realize that planetary systems commonly host multiple worlds with related characteristics. If K218b developed its hydrogen-rich atmosphere and possible oceanic environment under specific formative conditions, then other neighboring planets might have evolved in comparable ways. Discovering several potentially habitable planets orbiting the same star would offer valuable comparative data for studying Hyson world formation and evolution. The analytical techniques honed through K218b's study are already being adapted to examine other sub-Neptune exoplanets located in habitable zones around their respective stars. Each new planet observed contributes to a broader understanding of atmospheric diversity among these enigmatic bodies. Some exhibit clear water vapor signatures and complex chemical interplay, while others possess simpler atmospheric compositions. These distinctions may stem from different formation histories, stellar influences, or the natural evolutionary diversity that characterizes planetary systems. As researchers conduct comparative investigations across multiple Hyson-like candidates, emerging patterns are beginning to indicate which upcoming discoveries might be the most promising for biosignature detection. Factors including a planet's mass, orbital distance, age of its parent star, and the overall configuration of its system all appear to shape atmospheric composition in ways that scientists are only now beginning to grasp. This expanding body of knowledge will be essential for guiding future observational priorities as an increasing number of potentially habitable worlds come to light. The interdisciplinary character of K218b research continues to encourage partnerships between scientific domains that rarely intersect within conventional academia. Atmospheric chemists are joining forces with marine biologists to explore how life might endure within high-pressure aquatic ecosystems, while geophysicists and astrobiologists collaborate to model the internal structures of sub-Neptune-class planets. Meanwhile, computer scientists are creating machine learning frameworks specifically tailored to detect faint biosignature patterns hidden within noisy spectroscopic datasets. This fusion of specialized knowledge is producing insights that no single discipline could have achieved on its own. The ongoing investigation of K218b has become a true testbed for cross-disciplinary cooperation, illustrating how complex scientific puzzles demand a tapestry of diverse expertise. The success of this integrated model is now influencing how major research organizations coordinate projects and distribute resources when confronting other grand scientific challenges. The educational and cultural effects of K218b studies extend well beyond academic circles, spilling into public engagement and science communication. The potential to uncover life beyond Earth has captivated popular imagination in ways that ordinary astronomical findings seldom do. Around the globe, museums, planetariums, and educational institutions are weaving the K218b narrative into programs crafted to ignite curiosity about science and space exploration. For educators, the real challenge lies in conveying both the complexity and uncertainty of this research while keeping audiences engaged and inspired. The story of K218b exemplifies how science progresses at the frontiers of understanding, where each observation questions established theories and compels researchers to broaden their perspectives. Teaching such stories helps prepare future generations for a world where scientific knowledge continually evolves in response to new evidence and discovery. The global scope of K218b investigations has created unprecedented opportunities for international cooperation, reaching far beyond the planet's immediate scientific mysteries. Researchers across dozens of nations contribute observations, analytical tools, and theoretical frameworks to piece together an understanding of this distant world. The collaborative infrastructure built for this effort is already being repurposed for other large-scale scientific enterprises that require worldwide coordination and shared resources. These global partnerships demonstrate that fundamental scientific questions can bridge political, cultural, and ideological divides. The search for life outside Earth represents a unifying human mission, transcending national agendas. The cooperative spirit born from projects like K218b could serve as a blueprint for tackling other planetary-scale challenges that depend on sustained international unity and shared purpose. As scientists maintain their patient vigil for new data that might finally clarify the nature of K218b's atmospheric chemistry, humanity finds itself participating in one of the most profound scientific pursuits in history. Whether this planet eventually reveals evidence of life or merely stands as an extraordinary example of non-biological chemistry, its study has already revolutionized our view of what's possible and revealed the boundless ingenuity of human inquiry. The ancient light from K218's parent star continues its centuries-long journey toward Earth, encoded with spectral hints that may answer questions which have haunted human thought since our ancestors first gazed at the night sky. Each photon captured by our instruments serves as a messenger from a world so alien and remote that its very reality challenges our definitions of life and habitability. In the quiet intervals between observations, as our most advanced telescopes maintain their patient watch over this distant sphere, we stand poised between knowledge and mystery, between the chemistry we know and the unfamiliar potentialities that might dwell within the hydrogen-shrouded oceans of worlds beyond our solar neighborhood. The universe has already astonished us with the diversity of planetary atmospheres and the exotic chemical processes that occur under unimaginable conditions. Yet K218b may conceal the greatest revelation of all, proof that life can flourish in environments that stretch the boundaries of our imagination, bridging the cosmic interplay of chemistry and biology. This unfolding narrative continues daily within laboratories and observatories across the world, where determined researchers strive to extract every ounce of insight from data that pushes the edge of technological possibility. Each round of analysis exposes new layers of complexity. Each theoretical model opens fresh avenues of speculation, and every observation brings us one small step closer to resolving one of humanity's deepest questions. In this meticulous pursuit of cosmic truth, we uncover not only scientific progress but also a mirror of our most admirable human traits: our relentless curiosity, our devotion to understanding, and our bravery in confronting discoveries that may transform our perception of existence itself. The careful methodology required to verify these extraordinary claims underscores the rigorous nature of revolutionary science. Every single data point must be validated, every possible error meticulously ruled out, and every competing hypothesis examined before researchers dare to whisper that we might be glimpsing true evidence of extraterrestrial life. The statistical benchmarks separating an intriguing anomaly from a confirmed discovery have become the central focus of an unprecedented international scientific collaboration. The computational demands of this task are staggering. Cutting-edge spectroscopic analysis now requires algorithms that can discriminate wavelength variations accurate to mere parts per billion, separating real molecular signals from the countless interferences encountered across interstellar space. Each transit dataset contains millions of discrete measurements, each encoding a fragment of information about K218b's atmospheric makeup. Extracting coherent meaning from this immense sea of numbers calls for computational strategies that stretch the limits of today's hardware and theory alike. Machine learning systems engineered for astronomical use are being trained to recognize pattern combinations too subtle for the human eye, distinguishing authentic biosignatures from false positives or contamination from Earth's own atmosphere. These intelligent algorithms must compensate for everything, from minute thermal shifts within telescope components to the complex physics of starlight scattering through atmospheric gases over 124 light-years of distance. The precision required is so extreme it defies human intuition. Imagine picking out a single whisper in a roaring crowd of millions. That metaphor only begins to approximate the scale of the challenge faced by scientists searching for faint biological traces within the alien atmosphere of K2-18b. Yet beneath these staggering technical hurdles lies a deeper question, one that touches the core of what we mean by life itself. The molecules tentatively detected on K2-18b seem to exist at concentrations thousands of times greater than anything found on Earth. If these signals indeed point to biology, then we are witnessing life functioning on an unprecedented scale, operating beyond the limits of our terrestrial experience. The implications go far beyond detection. They challenge our understanding of biological systems, their energy requirements, and their efficiency. On Earth, marine phytoplankton release dimethyl sulfide, DMS, as a byproduct of metabolism, but even global production here pales compared to what might be happening on this distant world. If life is responsible for K2-18b's chemical makeup, it would imply biospheric productivity and efficiency so immense that Earth's own ecosystems would appear humble in comparison. Theoretical frameworks attempting to explain these findings are venturing into uncharted territory, where biology and planetary science converge in unprecedented ways. Researchers are exploring how vast oceanic ecosystems might operate beneath atmospheric pressures dozens of times greater than those found at sea level on Earth. Under such conditions, the physics of gas exchange between organisms and their environment changes dramatically, potentially allowing metabolic processes that would be impossible under normal terrestrial conditions. The chemical pathways open to hypothetical life within K2-18b's hydrogen-rich environment mark another boundary in our quest to understand biological potential. Terrestrial organisms are constrained by an oxygen-based chemistry, which defines what reactions are energetically viable. In contrast, a hydrogen-dominated atmosphere could permit entirely new metabolic networks, enabling forms of life that exploit energy sources unavailable on Earth. Laboratory simulations designed to test these ideas are producing astonishing revelations about the adaptability of life. Scientists are exposing Earth microbes to synthetic high-pressure, hydrogen-heavy environments, monitoring their survival and metabolic responses. The findings indicate that the line between habitable and uninhabitable may be far more flexible than we once believed. Some bacterial species not only endure such conditions but even demonstrate enhanced metabolic activity when immersed in these alien atmospheres. These results hint that the potential range of life-bearing environments in the cosmos may be vastly broader than our planet's example has led us to assume. These findings don't prove that life exists on K2-18b, but they demonstrate that the environmental conditions on high-end worlds might indeed be compatible with biological processes. The experiments are expanding our understanding of life's fundamental requirements while providing crucial context for interpreting the atmospheric observations. The isotopic signatures hidden within K2-18b's spectroscopic data offer another potential pathway toward understanding whether the observed chemistry reflects biological or purely physical processes. On Earth, living organisms often preferentially incorporate lighter isotopes of carbon, sulfur, and other elements into their biochemical structures. This isotopic fractionation creates distinctive patterns that can serve as fingerprints of biological activity even when the organisms themselves remain invisible to direct observation. Detecting isotopic signatures in exoplanet atmospheres requires pushing spectroscopic techniques to their absolute limits. The generation of magnetic fields in subneptune planets like K218b is governed by mysterious processes unfolding deep within their hidden interiors. Under immense pressure, ordinary materials could transform into exotic forms of matter with strange electrical properties, unlike anything found on Earth. Some models even propose the existence of superionic ice, a bizarre state where hydrogen ions move freely through a rigid oxygen lattice, enabling magnetic dynamos that function by rules unfamiliar to our solar system. If K218b possesses such a magnetic field, its interaction with the planet's vast hydrogen atmosphere could create chemical environments found nowhere else in the cosmos. Charged particles trapped within magnetic lines might trigger reactions that reshape atmospheric chemistry in ways that terrestrial science has never encountered. Understanding these forces is crucial if we are to distinguish between biological signatures and purely physical phenomena hidden within that swirling hydrogen sea. The search for similar subneptune worlds has accelerated as astronomers realize how vital these planets may be for astrobiology. Dozens orbit within their stars' habitable zones, and each new discovery expands our growing catalog of atmospheric diversity. Some display evidence of water vapor and complex molecular chemistry, while others appear simpler, dominated by hydrogen and helium alone. These differences could arise from distinct formation histories, unique stellar environments, or the unpredictable pathways of planetary evolution. Comparative studies are beginning to reveal patterns connecting planetary mass, orbital distance, and stellar age to the complexity of atmospheric chemistry. These findings are helping scientists identify which worlds may be most likely to harbor conditions suitable for life. The effort to understand K218b has united experts from fields that rarely intersect. Atmospheric chemists collaborate with marine biologists studying Earth's deep oceans. Planetary scientists consult with biochemists to imagine alien metabolisms, and computer scientists design algorithms capable of teasing faint signals from oceans of astronomical data. This blending of disciplines has created insights no single field could achieve alone. The challenge of interpreting K218b's atmosphere demands mastery of everything from quantum interactions between photons and molecules to the ecological dynamics that govern stable environments. The technologies born from this research are already transforming life on Earth. Ultrasensitive spectroscopic tools now serve in medicine, environmental monitoring, and industrial control, while the data analysis methods designed for Webb's faint exoplanet readings are reshaping fields from seismology to finance. International cooperation surrounding K218b has forged scientific alliances that transcend borders and politics. Researchers from dozens of nations share data, resources, and expertise, driven by a single question that unites humanity. Are we alone? The spirit of collaboration born from this search could one day serve as a model for tackling global challenges far closer to home. Meanwhile, the story of K218b continues to inspire classrooms and planetariums worldwide, showing how the pursuit of cosmic truth fuels curiosity and wonder. Each refinement of observation reveals more complexity within K218b's atmosphere, new molecules, new mysteries, potential traces of hydrocarbons, nitrogen compounds, and sulfur species now join the list of candidates hinting at biological or exotic chemical processes. The planet's atmosphere is no longer viewed as a simple hydrogen shroud, but as a dynamic, layered system governed by unfamiliar principles. Because K218b completes an orbit every 33 days, its atmosphere may evolve dramatically as it moves through different phases of its orbit. These fluctuations could influence chemical stability, molecular production, and the visibility of potential biosignatures. Every observation captures only a fleeting moment in a living, shifting system, one that might change with a rhythm reminiscent of seasons or even cycles of life itself. And so, as we stand at this extraordinary threshold in human exploration, gazing toward the constellation of Leo, where K218b silently circles its faint red sun, we confront both the profound and the possible. Perhaps this hydrogen-shrouded world conceals the first verified evidence of life beyond our solar system. Or perhaps it simply represents the most intricate and unfamiliar chemistry ever witnessed among the stars. Either way, K218b has already expanded the boundaries of our imagination and reshaped our understanding of what worlds beyond Earth might be. The soft, ancient light that carries those elusive molecular signatures continues its long voyage through interstellar space, threading the darkness to reach our waiting instruments. With every orbit and every refinement in observation, we inch closer to answers that could redefine the human story, answers that may transform how we perceive life, existence, and our fragile place within the cosmos. Until the next chapter of this cosmic journey unfolds, may we keep our eyes lifted toward the heavens, our curiosity undimmed, and our sense of wonder alive. For the universe still holds secrets far greater than we can yet comprehend.